Well, hi everyone, and greetings from Northern Michigan. This is Bob the Science Guy. I woke up this morning and I just got the urge to do some math. So, let's talk about the relationship between sine and cosine and something called the small angle approximation. Now, today what I'm going to do is I'm going to put it up on the board so that you get the didactic portion of it. Then we're going to go over to the desk and I'm going to use the slide rule and we're going to demonstrate it physically, so that you see the relationships between sine, cosine, a little bit of tangent, and most importantly, something called the small angle approximation. So let's cue up the music and get going. Okay, so let's get started and see if we can understand this a little bit. You're all familiar with what we call the unit circle. The unit circle is a circle with radius of 1, and we use it to kind of describe sine, cosine, and trigonometric functions. So, we've got three angles here. We've got a right angle, we've got angle alpha, and we have angle beta. Now, let's look at angle alpha first. What's the sine of angle alpha? Well, the sine of angle alpha will be the opposite over the hypotenuse, so A over H. The cosine of angle alpha would equal the adjacent over the hypotenuse, so B over H. Now, what's the relationship between angle alpha and angle beta? Well, let's go ahead and have a quick look. If we look at angle beta, what is the sine of angle beta? Well, it's side B over the hypotenuse. How about the cosine of angle beta? Well, that's the adjacent over the hypotenuse, which is there. So this is the first of our very important relationships. The sine of alpha equals the cosine of 90 minus alpha. That's the same thing as saying the cosine of beta, because angle beta is 90 degrees minus angle alpha. See how that works? Pretty cool, huh? Likewise, the cosine of alpha equals the sine of 90 minus alpha, which again is beta. But we're going to write it like that because that's the way that we need to think about it. These are complementary angles. If you look at this angle, its complement is that angle up there, which is 90 minus the original angle. But let's look at one more very important relationship between sine and cosine. And that's something called the Pythagorean identity. Now, we're all familiar with this. That would be the Pythagorean theory. Now, in a unit circle where the radius is 1, we know that this side is the cosine of alpha, and this is the sine of alpha. We recall that from our first talk about sine and cosine. So we can rewrite this a little bit. We can say the sine alpha squared plus the sine beta squared equals 1. That's called a Pythagorean identity. Now, one of the things that you can do with this that's very important, and it's so important that we're going to put it over here. Is that we just rewrite it a little bit. So, sine squared alpha equals 1 minus sine squared beta. sine square beta equals 1 minus sine square alpha. Likewise, we can say that cosine squared alpha equals 1 minus cosine squared beta. Cosine beta equals 1 minus cosine squared alpha. Now, what does this mean in the real world? Okay, so say we have an angle 75 degrees. We'll say that we can read the sine of 75 degrees directly off of a piece of paper. What's the cosine of 75 degrees? Well, the cosine of 75 equals the sine of 15 degrees, because the cosine of any angle equals the sine of 90 minus that angle. 90 minus 75 is 15 degrees. See how that works out? So for example, when you're looking at the sine scale on a slide rule, what you'll see is a black 75 and you'll see a red 15. That means that the number above it is the sine of 75 degrees and it's the cosine of 15 degrees. Now if you look down the slide a little bit, you might see 15 and 75. That would be the sine of 15 and the cosine of 75. You see the relationship between the two? So let's go over to the desk and do this on the Aristo slide rule so you can see the relationships, and then we're going to come back and talk about something called the small angle approximation. So let's go over to the desk. Okay, so let's go ahead and have a quick look at the slide rule here. Now, the scale that we need to look at for sine and cosine is the S scale right here. And then we're going to read it against the D scale. Notice that we're familiar with the C and D scale, and they're exactly the same. The D scale is all we need on this, so let's just go ahead and get rid of the slide. It just adds confusion and clutter. So let's just take it right off. Okay, so let's go ahead and take a look at our first identity, and that is that sine alpha equals the cosine of 90 minus alpha. And we'll look right here. So that would mean that the sine of 25 would equal the cosine of 65. And these are in degrees. So let's go ahead and have a quick look and see what that is. So we'll put our cursor right there with our hairline right over. We're going to come up with 0.412. Looks like about 4.2 or 4.25. So let's go see what that comes up to on the calculator. That's not too bad. We came up with about 0.4225, and the answer is actually 0.4226. And that is the correct answer to 4 significant digits. That's the beauty of having a 20-inch slide rule. Now, just for completeness, let's go ahead and figure out the cosine of 65 degrees. And there it is, exactly the same. Let's find the sine and the cosine of 40 degrees. That's not sine times cosine. I just want to know the sine and the cosine of 40 degrees. So what we'll do is we'll bring the slide rule right over here until we see 40. And we'll put the cursor right over it. And then we will read off the sine directly above it. So that's 0.642. And we'll write that here. Okay, so that equals the sine. Now let's go down here and find out where the 40-degree mark is, and it's right there underneath 50. Now if we read up here, we'll get the cosine of 40 degrees, and that would be 0.76. So there are our two values. So let's go ahead and compare that to what we get on the calculator. So the sine of 40 degrees going to be 0.6427, and we got 0.642. The cosine will be 0.766. We got 0.767. Again, not bad. 3 significant digits, pretty darn close. Now I put the slide back in because say we wanted to multiply the cosine of 40 degrees by 8. We just put the index line right over our cosine, which we read directly off the D scale here. Go right down to 8, and there's our answer. Okay, so the question becomes, where do we put the decimal place here? If you're reading an answer on the S scale, the sine or the cosine is going to be 0 point something 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 something. If we're going to multiply that by 8, we look at the number there, it's 0.612 perhaps, or 613, what's on the scale right now. Now, since we started off with a number that was 0.76 something, and we multiplied it by 8, this is going to give us an answer of 6.12, it looks like. So that would be about reasonable. That's where the decimal place would go. All right, let's have a look at the Pythagorean identity for a moment, because this will help us with our next step here. The Pythagorean identity, as you recall, is sine squared plus cosine squared equals 1. Now, rearranging this a little bit, sine squared equals 1 minus cosine squared, and conversely, cosine squared equals 1 minus sine squared. Now, moving this over, we know that sine equals the square root of 1 minus cosine squared, and we know the cosine equals the square root of 1 minus the sine squared. Now, if we look on the S scale, that equals the sine of x. It also equals the cosine of 90 minus x. What would happen if we had a scale that was 1 minus x squared? That could be quite useful. Let's have a look at the slide rule again. Now right here we have the S scale. It's on the bottom. And if we look down at the end here, we see that in black, that represents the sine. And in red, it represents the cosine. Look right above it. There's the square root of 1 minus x squared. Now you don't see this on many slide rules, because this is what's called the Pythagorean scale, or the P scale. Now if you look at an American slide rule like my father's KE, you won't see a Pythagorean scale on this. It's not on the other side either. The P scale is generally only found on European slide rules, and the Aristo Studio is a German slide rule. Now, if you're going to be doing trigonometry at all on your slide rule, I would suggest finding one that has a P scale on it. And I'm going to show you why it's useful. Now here we see the paired angles. If we put the cursor here, we're going to get the sine of 25 degrees, and we'll get the cosine of 65 degrees, its complement. So let's go ahead and read up here and see what we have. For 25 degrees, the sine would be 0.42, and I'd say that'd be about 0.425. And if we do this on the calculator, that's pretty good. We're almost to 4 significant digits. Now, to find the cosine of 25 degrees, what we need to do is we need to come down to about here, because that's where the red cosine would be, about halfway between 20 and 30. You notice how tight this is in here. And we can come up and get a reading. It looks like it's going to be 0.906 or so, and that's not too bad. Imagine trying to do this with 80 degrees. That would get a little tight, wouldn't it? This would just be very difficult to do. So let's go ahead and have a look at something here. Let's take 80 degrees. Let's get the sine and the cosine of 80 degrees. Now I would read the sine of 80 degrees as perhaps 0.985 maybe. And that's not too bad. Let's go see where the cosine of 80 degrees would be. Cosine of 80 degrees would be way down here. And then we would read up, and that would be 0.1736 perhaps. And we didn't do too badly with that. But we also had to move the slide. So let's go ahead and redo that a little bit. One of the things that I couldn't help but notice down here, we're down around 80. That's 70. That's 90. You see how tight that space is in there? Compare that instead down here. Look how far it is to go between 10 and 15. Look at all this space down here. This is a lot easier to use. Now, the other thing that I told you about earlier was that the more you move a slide, the more error you can get. So let's look at something here. How about instead of starting way down here, let's just go right here. And we're going to read off the cosine of 80 degrees directly. And if you go up there and do that, that's going to be 17.36, I think is what we said that would be. 17.36. Well, what's the cosine? The cosine is on the p scale right underneath it. Notice that this is in red, which means that it's running backwards. Here's 0.98, here's 0.985, and over here would be 0.99. So what we have to do is we have to read up on the p scale 0.98, 981, 982, 983, 984, 9845, 9848. Let's go see how that turned out. Pretty much exact. I'm pretty proud of that. But you see how we could get both of them at the same time without moving the cursor. As you may recall, there's a measurement of angular size called a radian. Every circle's got a radius. Now normally there'd be 360 degrees in that circumference. However, if you break up the circumference in lengths of the radius, you get something called radians. The formula for the circumference of a circle is 2 pi r. So there are 2 pi radians in 360 degrees. Now here's where this is handy. Now let's look at a tiny angle. Here's 7 degrees. That represents 0.12217 radians. And the way you do that, of course, is you take the degrees divided by 180 times pi. That's the conversion. Now, what's the sine of 7 degrees? It's 0.121869. Notice how close these are. What's the cosine of 7 degrees? 0.99255. Notice how close that is to 1. Now, if you're looking at 3 significant digits, both of these would be 1.22. If you're again looking at significant digits, this would be 0.993. That's very close to 1. So let's go back to the board and have a look at this for a second. The second part of this is called the small angle approximation. When you're dealing with small angles, and they're not that small, 10 degrees, you're starting to see big effects. We just saw it with 7 degrees. But let's go over what the small angle approximation is. It says that for small angles, the sine equals the tangent equals the angle in radians. So as we just saw with 7 degrees, the sine was very close to what the radians were. And if you do it with the tangent, using that same degree of radians, you'll see the tangent is approaching the angle in radians. What about cosine? The cosine approaches 1. Now, one of the things that might be an interesting exercise is to see how far off this is. You'll be surprised at how close it really is. Now, we were dealing with an angle of 7 degrees. What if we're dealing with something like the stellar parallax of Polaris? I don't know if you recall what that is. The stellar parallax of Polaris was 7.54 milli-arcseconds. Now, what's an arcsecond? Now, many of you saw my video measuring the curve of the Earth across the lake in my backyard. That was the curve of the Earth over 2,500 feet. Now, if you take an American quarter right there and hold it by that phone box on the other side of the lake, and I were to measure that angle from my side of the lake, we're talking about 6 arcseconds. Going back to our coin-based measuring system, and by the way, this is a great time to join the channel. That's an American dime. It's just around 1 centimeter in diameter. If you looked at a dime from a distance of 2.5 miles or 4 kilometers, that's 1 arcsecond. The parallax of Polaris, with a base leg of almost 100 million miles, is 7.54 1,000th of an arcsecond. Now, I don't know what's more mind-boggling to me. The fact that there are angles that small, or that we can measure them within 10%. Science is freaking awesome, isn't it? Now let's head back over to the slide ruler and see how we deal with small angle approximations on a slide rule. It's a very elegant solution, and I think that you'll find it interesting. So let's go have a look. Okay, so when dealing with most angles, we're going to use the S scale to get the sine and the cosine. And then we're going to use the P, or the Pythagorean scale, to find whatever it is we didn't look for on the S scale. So for example, if we were looking for the sine on the S scale, the cosine would be on the P scale. If we were looking for the cosine on the S scale, the sine would be on the P scale. Now, there's another scale up here I want to show you, and that is this ST scale. The ST scale is the small angle scale, and you see it goes all the way down to 0.55 degrees. Now let's go ahead and have a look at something real fast. If we look down here on the S scale, you'll notice that the 1 mark is at 5.5, 5.6, 5.7, about 5.74 degrees. What's special about that? Why would it stop there? Especially since we saw that it started, the small angle approximation started much higher, maybe even all the way out here to 10. Why did they choose 5.74 degrees to start this? Well, let's go ahead and have a quick look. Now, I don't know if you recall me saying that, but for the most part of the S scale, the sine and the cosine are going to be 0 point something, 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 something. Okay, let's go ahead and see an example of that. So let's go back over here to our calculator real quick just to do it. So let's go 5.8 degrees. And we're going to take sine of that. So there's the sine. 0.10105, or 0.6 if you round it. Notice that that has the form of 0 point something, 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 something. Now let's look at 5.75 degrees, and we're going to take the sine of that. Notice anything here? We have 0.10019. Okay? Where did we cut off? 5.74. So let's go to 5.73. What's the sine of that? Whoops. Look at that. Now our form is 0.0 something, 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 something. 5.74 degrees is the cutoff for where that 0 pops in. That's part of the elegance of a slide rule. In this particular instance, it's keeping track of where your decimal point goes. Now let's pick a spot somewhere here in the middle of the slide rule. Okay, so right here in the middle of the slide rule is 2 degrees. Notice it's got a red 88 underneath it. See how that works on both ways? So let's read down and see let's see what the sine of 2 degrees would be. We'd come down here and it would be, let's see, 0.031234. 0.0448. And there we go. 0.0348. Or actually almost 0.0349. Now what would the cosine of 2 degrees be? I don't think folks would be too upset with you if you kind of rounded that to 1. Do you? Okay, so let's go ahead and put the sine of 2 degrees up again. It's 0.03489. Now, just for laughs, let's find out what the tangent of 2 degrees would be. The difference is 3/1000ths. That's close enough. Now, while we're at it, let's go ahead and see what the radians are. So 2 divided by 180 equals times pi equals. So you see how they're all coming together? Now that's for 2 degrees. Wonder what it is for 0.75 degrees. For 0.75 degrees, I'm reading 0.031, it looks like. 0.031. I'm happy with that. Let's see what the cosine would be. I'm happy with calling that 1. Let's see what tangent is. 0.0131. I'm happy with that too. And finally, let's take the radians. 0.0131 again. See how they're all coming together? You know, I don't know about you, but listening to a lecture about that would have kind of gone over my head and in one ear and out the other. However, when you take the slide rule out and you actually physically do it with your hand, it seems to make a lot more sense to me, and it made something click inside of me, and now I understand it. I hope that you gained a little bit of understanding with this as well. This is one of the reasons that I'm looking into things like the slide rule, because they're great teaching aids. They gain understanding rather than memorization. So, this is Bob the Science Guy signing out from Northern Michigan. Thank you again for stopping by, and make sure you support the channel. We've got more good things coming, and I'll see you again soon.